And we're continuing. Our next guest from the science world, Vladimir Spokojny, who is not only a renowned expert in mathematical studies and sciences, but he's also a mentor for a lot of promising researchers. Today, he is going to talk about the theoretical foundation of AI and how to correctly assess the results and the correctness of the AI-made decisions. The professor of the Humboldt University, the head of the Stochastic Algorithm Lab and Parametristic Lab of Weierstrasse Institute, the head of AI in High School of Economics, Vladimir Spokojny, the theoretical foundations of AI.
Hello to everybody. I'm very happy to be here. My talk will be a little bit special. No pictures, no applications. I will speak about foundations. And I hope that I can provide some messages which are important also for understanding of the problem of artificial intelligence. So one of the main questions is trainability and reliability of the model of artificial intelligence. This means we train our model for solving a specific task. And we want to understand, is the decision made by artificial intelligence system is reliable, and how reliable. Can we trust to this decision? Okay, so this is the goal, and now I will start to explain the main issues of this study. So maybe the most important issue, we have typically very complicated data and huge amount of data. But at the same time, we have very complicated models with a huge amount of parameters. So, and the more complicated data we have, the more complicated models we apply. And number of parameters grow exponentially with the sample size, with the amount of data. So this is a kind of paradox. The more data we have, the more complex our problem is to train. And then the question is it possible to give some theoretical guarantees for our decisions? Because we have so many parameters which we cannot estimate efficiently. This is exactly the question which I would like to study, and in particular, I would like to see some theoretical guarantees of the decision made by the AI systems. Okay, so I will illustrate most of the result by a simple model, which is nonlinear regression. And in fact, the first method for nonlinear regression was applied by Gauss for astronomical applications. He solved a practical problem of finding a planet on the sky from few observations. So astronauts lost this planet, small planet, and Gauss spent half a day to find it by numerical methods without any computer, just on the sheet of papers. And this model is now a leading model for deep neural networks. So we see this model survives from Gauss to up to now, but the number of parameters grows, as said, exponentially. So for Gauss, it was just a few parameters which coded the trajectory of the planet. And for DNN, we have parameter theta in this equation. Unfortunately, pointer doesn't work. So you see the equation, regression equation, yi is m of xi theta, and theta is a parameter of the deep neural network which codes the whole architecture. This means this parameter is really huge, dimensional. And now the question is, can we train our deep neural network from the labeled data? Every yi is a label given to the input vector xi. Okay? So this means small theta is a vector in the capital theta, which is a subspace of p-dimensional space where p is extremely large. Okay? So this is the setup. Now, what we want to do, we want to study the situation when p is extremely large. So you can say infinite. And the sample size n could be big or moderate, but it's by far smaller than the dimension of the parameter space. And we want to get some theoretical guarantees, and to do this, I would like to introduce the notion of effective dimension of the problem. And this notion is a key to understand the essence of what is going on with all models of artificial intelligence. Okay? So now a very crash introduction in statistical learning theory. I expect not many of you are familiar, so I don't expect this at least, and I will give you a very short list of notions and definitions, and then I will try to illustrate the main results in these terms. So what is a statistical problem in general? So we have some objective function, capital L, which depends on the parameter v. Okay? Then the typical training procedure is a solving of an optimization problem. We try to maximize if it is log likelihood or minimize if it is a cost of this objective function. So v tilde is a point of maximum of the log likelihood, or point of minimum of our cost function. Okay? Now we define the target, so or true value. True value is v star, and this solves similar problem, but given in terms of the data distribution. So data is random, and if we would know the distribution of the data, we can solve this problem efficiently, and then v star will be the true value. So it minimizes what we would like to minimize in average. Okay? So then the main issue in statistics is to understand the relation between these two problems. The first problem is practical, what we are really doing. The second problem can be called oracle problem. This means we define the true value which corresponds to the data distribution. And actually, the whole statistics is a way to understand what is v tilde minus v star, or L of v tilde, so the maximum of the problem minus L of v star. So this is a very brief definition of learning theory. So the whole learning theory is these two lines, okay? The essence. Now, I introduce few notions to describe the main results. This is all what you need to know to look the results. So first two lines, truth and the estimator, are the same as the previous slide. Then we introduce extremely important notion of the Fisher information, or Fisher information matrix, F. So this is a Hessian of the expected log likelihood at the true point. So this is a very important notion which is used both in statistics, learning theory, information theory, physics, everywhere. So this is information, but information about the vector. of parameters. Therefore, this capital F is a p times p dimensional matrix, really huge. Then all the rest is defined more or less in terms of this Fisher information matrix. In particular, effective sample size corresponds to the smallest eigenvalue of this function. Then we need to measure the noise in the data. And this noise is measured using the score function, which is defined as a log likelihood minus its expected value. And finally, we define the most important notion, which is effective dimension. And this is something like noise divided by the signal. So you see it is a trace of the variance of the score, variance of the noise, multiplied by the inverse of the Fisher information matrix. So this is all the definitions we need to understand the essence of the learning theory. Okay? So now I show you very briefly the overview of the main results. And then we will proceed with the conclusions. So this is extremely simple to understand and extremely difficult to study. So first result is called concentration or consistency. And this result requires that the effective dimension of the problem is smaller than effective sample size. And under this condition, we can say that V tilde is indeed close to the V star. This means what is the result of training of our model or deep neural network is close to the target, to the truth. And this can be again measured in terms of the efficient dimension and Fisher information. So this is the first result about concentration, which is extremely important. And it gives the view on the essence of the statistical problem. So once again, I show you the definitions. So we have Fisher information, we have effective dimension, and we have effective sample size. Everything is given in terms of our objective function, log likelihood, and with this notion, we define something like law of the nature. The model can be trained nearly consistently only under the condition that the effective dimension is smaller than effective sample size. So maybe most of you are familiar with this, and intuitively it's also clear. We cannot estimate more parameters than the number of observations we have in our disposal. And this is exactly this law. If you want to do a kind of inference, this means if you want to study singular elements of your, say, network, particular edges or nodes, you need even stronger condition. So, and this is given in terms of the Fisher expansion. It tells that the effective dimension should be smaller than square root of the effective sample size. And for some other problems, you need even stronger conditions that effective dimension is smaller than sample size to the 1/3. So what we see here, different type of conclusion requires a critical dimension condition, which is indicated here in this result. And in all this result, you see that effective dimension of the problem cannot be too big. Now we are in the trouble and the question. So how it can be that we have our model, which is highly overparameterized. Yeah? So we have models with billions of the parameters. And the theory tells us It could not be. We cannot train this model by data because we need this condition. P is smaller than n. How we can avoid this? How we can get theoretical guarantees? The standard approach here in statistics and learning is to use structure. So what we say, a real structure is simpler. So we have a lot of parameters. Most of these parameters actually are not important, can be thrown away. This is the structure of the model. And this is exactly what helps us to reduce the effective dimension. So effective dimension can be viewed as the complexity of the model, real parameters, which we really need. Not all the parameters, but those which we really need for describing our model. And how we can do this? Typically, the structure can be expressed using the penalty function. So this is a mathematical way to do this complexity reduction. So we consider penalized log likelihood, where our objective function is penalize something which means the complexity of the model. This means when we maximize this expression, so L of V minus penalty, we don't like to get a very complex model because penalty becomes huge. So this is the idea of reduction of the complexity, and typical examples of the penalty could be quadratic or rich regression or L1 norm, which is known as lasso regression. There is a lot of other proposals. Then, so what we get out of this, we get, instead of three optimization problems. One is which we really train now with penalized log likelihood. We maximize this expression, which means fidelity term minus complexity given by the penalty. Then we have what is called population counterpart, V star G, which is the same maximization of the expectation, and V star is the original truth. And now we want to understand the relation between V tilde G and V star. Okay? So this is the idea of reduction of complexity using penalization. So in the study I described here, actually the answer is given in a similar way. It is written below. Actually, if the penalty is smooth, you can describe the bias introduced by the penalty using the gradient of the penalty, which is similar to the noise. This means we have two sources of corruption, one due to the noise, one due to the penalty, and then each of them can be described by the decomposition, which I call Fisher decomposition, Fisher expansion. Good. Finally, you can put all together. Maybe I skip the details and show you the theorem, which is written here. And this theorem tells us if we have our trained model, V tilde G is our trained neural network. V star is the truth, what we want to achieve, which is not known because it relies on the unknown data distribution. Then we have two leading terms. One describes the impact of the noise, and the second term describes the impact of the penalty. Okay, and then we have in the right-hand side the remainder, and this remainder has the order, which I explained already, P over square root of n, where P is the effective dimension of the problem, which is now reduced due to penalization. Because in the penalization, so maybe I show you what's happening here when we introduce the penalty. We replace the original Fisher information matrix by the FG, where Fg involves the Hessian of the penalty. And this is exactly the idea of reduction of the complexity. If we have a structure, it can be described by the penalty, and this penalty actually serves for reduction of the complexity of the data, and then we can achieve the goal that the effective dimension of the problem after including the penalty is smaller than the sample size. So this is the key observation for the theory. So what is funny, so the main tool for this theorem is the perturbation optimization theory. And actually it connects two optimization problems. One is based on the function f, then we have a perturbation which could be linear, like here g is a linear perturbation of f, or it could be smooth. And then we need to understand the relation between the solution of original problem and the problem after perturbation. And first result of this form was established by Newton. So we see, people like Gauss and Newton made the first contribution to the modern artificial intelligence. Okay. So this is the result. So this is a similar result for smooth penalization. So this is a list of messages about what I said. And maybe the most important message of the theory is that the problem with statistics, which is called curse of dimension, which means that the result in high-dimensional statistics are very poor if the dimensionality growth should be replaced by the notion of the critical dimension, which means that the effective dimension of the problem is smaller than the effective sample size. Okay, now I would like to illustrate this by two examples. So very simple. So I consider deep neural network. So in this example, it's not deep, only one hidden layer. But it's just to explain the ideas. Otherwise, it can be extended to multi-layer problem as well. So we have our data, labeled data. Why are our labels given the input vector x? And basically, in this case, the whole parameter vector is a matrix W, which connects the input x and nodes of the hidden layer. So the W is the matrix of edges. Okay, then the objective function or log likelihood is a sum of misclassifications in this particular example. And this depends on the vector x1, which is activating function applied to W of x. So we want to recover the matrix W from our input data. So if we have high-dimensional input and a lot of nodes in the hidden layer, then this matrix could be very large. Okay? And now we want to understand what is the effective dimension of the problem. In this particular case, it's actually relatively clear what is the effective dimension. It's the number of edges which are non-zero and significantly non-zero. Okay? But how we can achieve this? This problem, unfortunately, is highly over-parameterized, non-concave, non-smooth. But the most important issue is actually lack of identifiability. This means the nodes in the hidden layer can be exchanged together with the AIJs, and this will give you the same neural network. Okay, so the order of the nodes is not unique, and this is probably the main issue for the theory. And what is suggested is that we introduce a structure in the neural network. So this is the question: how the structure can be introduced? Very simple way. So what we are doing, we say the first node in the hidden layer is the most important. The second is less important, and so forth. Yeah. The number of the node means importance. And then, for every edge which we effectively use, we pay a penalty function which increases with the number, with the corresponding number of the node. This means any edge to the first node costs nothing. But if you draw the edge to the node number 10, it will cost much more. And if we do this, then it leads to the penalty, which is a penalty function which is drawn in the first line, where this SMJ are factors which grows with a number m and number g, most important number g, polynomially. And if we introduce this penalty, this is a kind of mystery, which what is happening, then the effective dimension of this problem becomes finite. Even if you have huge number of nodes, effective dimension after this penalization can be controlled. And this is explained why a real neural network can be trained. Because, in fact, after proper regularization, these are the problems with not so big effective dimension, and therefore this magic condition, critical dimension condition, is fulfilled. The other example is sparse estimation. So for this example, what is assumed is that our output depends on the input vector theta, which is sparse. This means only few coefficients are important and non-zero. The other are zeros, and then you can have a huge dimension of the vector theta and only a few observations wise. So this is a typical statement of the problem, and a classical solution is a loss solution, which means we add L1 penalty. Unfortunately, this approach does not explain the effective dimension of the problem. What is the effective dimension? So intuitively, it's clear. If you have sparse vector, effective dimension corresponds to the sparsity, number of non-zero coefficients. And then we want to apply the theory and derive this effective dimension. But it doesn't apply to lasso because L1 norm is not differentiable, non-smooth. So, but if you redefine this penalty using different proposals, you can use spike and slap penalty, or you can use interaction penalty. Maybe I jump over all these examples. But then you can redefine the Fisher information and get the result which gives you, again, the effective dimension corresponding to the sparsity. So this is two examples of applying this theory. But in fact, we are working very intensively on this, and current list of examples which we already considered includes many real applications like multi-view models, error and operator models, nonlinear partial differential equation, matrix completion and recovery, Gaussian mixture, and many other. So I think I can conclude at this point. And again, I would like to stress the most important message, which says that stable and reliable statistical learning is only possible under critical dimension conditions. This means effective structure of the model should be such that the effective number of parameters is smaller than effective sample size. Okay? And then, if we study the procedure, any training procedure, the main question is whether this training procedure is structure adaptive, whether this procedure is able to recover the underlying structure. So, I think this is a message, but it's only starting point, and we have a lot of problems which are still under investigation, and all of them includes the issues of identifiability, non-concavity, non-smoothness, etc. And yeah, so everybody is invited to also to contribute. Okay, I think I am done.
Vladimir Spokojny, ваши аплодисменты.
Vladimir Spokojny, a round of applause for you. Vladimir, thank you very much. If I may, I would like to ask the questions in Russian. We have a few questions from the audience, but first I would like to once again thank you for this amazing lecture. We have so many people in the audience eagerly listening to your presentation and enthusiastic about such fundamental areas. I really felt like I was back at school, back in college. I hope you're not going to test me on stochastic elements. So taking this opportunity, I would like to ask you a few questions from the audience. So many questions and so little time. A question, a particularly difficult question. What are some of the areas of research in AI theoretical foundations that are the most promising in your opinion? It is indeed a very difficult question. We do have a lot of smart people in the audience. Well, I think my entire lecture was my attempt to answer this question. What I'm interested in is the boundaries of AI. Sorry, I'm speaking Russian. Is that okay? I hope it's okay. So we want to figure out what are some of the problems that AI can solve, and can we rely on these solutions? This is the key issue for me, and I would like to find a mathematical explanation of it, a mathematical basis for it. So what I was presenting today was a description of one step toward it. Thank you very much. Thank you for the fascinating lecture, for such a deep dive into it. Vladimir Spokojny, this applause is yours. Professor of Humboldt University, head of Stochastic Algorithms and Non-Parametric Statistics Lab of Weierstrasse Institute, academic supervisor of Theoretical Foundations of AI Models of the Higher School of Economics. Vladimir Spokojny, thank you very much.